So good afternoon, everyone, or good morning, depending on where you're connected from. So today we are actually kicking our 2023 GEO at EFR webinar series. And we've chosen quite an ambitious topic, which is plate boundaries. And to start, we are a bit spoiled because our guest speaker today is Dr. Abdelkrim Aoudia from the International Center for Theoretical Physics. And he's going to talk to us about active deformation and earthquake transients using case studies from the Alpine Himalayan region. And before I give the floor to Karim, I just want to let you know that at the end, Dr. Tapari Ram will convene the question session. So, and Ari is a colleague of Karim, of course. So, Karim, the floor is yours.
Okay, thank you very much. I hope that you hear me, right?
Yes, we do.
Okay, this is great. So first of all, I would like to apologize because I had to put some slides together at the last minute. So if there is any problem within my PowerPoint, I think that you need to excuse me. So I will be myself, I'm a big fan of active deformation studies within continental regions. And recently I moved to subduction zones, but I think that the fun is in continental regions anyway. So the beautiful picture that you see here is our campus. I mean, we're basically in a wonderful place. So anyone that is connected is most welcome to join ICTP and come and visit us. If you came already, then come again. If you've never been here, just come and visit us anytime. Just drop an email before. So, well, let me just move on. So I think that we've come a long way in monitoring and modeling earthquake deformation. So myself, I always try to look at plate boundaries within the continents and also have a good feeling of what is going on at the scale of the active faults. What you see on the left are basically conceptual models of what we think might be going on within plate boundaries within the continents. You may have, I mean, I work within a very theoretical institute. So I mean, I keep telling to my colleagues that are working in string theory or high energy physics that we earth scientists are lucky because we have end-member models. I mean, so if we do simulations or we do physics and we do quantitative stuff, then if our results do not get within those models, then I think that we're maybe selling bananas to some extent. But yes, we have constraints, and data are extremely important in anything that we do. So if you move from a distributed deformation scheme to a localized deformation scheme, I think that what would allow you to do this is definitely chasing the deformation in a quite continuous way, both within the interseismic and I will show examples within the post-seismic deformation that do clarify the issues in which model you are. At the same time, I mean, with all the timing the time that has passed over the years, we keep knowing and discovering things about how faults behave. And they are within a broad spectrum of processes that basically span from the aseismic slip, which is a time-dependent deformation, to super shear earthquakes. And talking about Turkey, the super shear earthquake has been defined specifically after the Izmit 1999 earthquake. This refers to just to bring Turkey in the middle. So myself, as a background, I'm a rock mechanicist. I did continuum mechanics in the beginning, and then I did engineering in rock mechanics. So in my engineering, I was always informed that if you have constant loading in your rock mechanics experiments, you may have transients that are popping up within the system. And when I started my PhD in the beginning, this goes back to 1994, I was quite amazed by the fact that the earthquake cycle at that time was treated in a quite simple manner. That was quite nice, quite easy, but very understanding. It depends on your aim, on the aim that you would like, I mean, on the goal or your objectives within your research. And very recently, I mean, my transient feelings as an engineer were satisfied by this. This is the way that we view now the earthquake cycle nowadays, and this goes back to the work of Giulio Di Toro in 2012, in which you see that a fault is exhibiting different types of behavior prior to the earthquake, during the earthquake, and within the post-seismic phase and up to the interseismic phase. And these are processes that are extremely important to that would give you hints on how a single fault is working and how a fault might act within an earthquake sequence, and how a fault may, and how this could even clarify on how our plate boundary is working. And talking about transients, and I mean, this is the way we see earthquake cycles nowadays, I mean, since 2012. And the funny side of the story here is this is transients in transients, and this is very fresh from Roger Bilhem after the Turkish earthquake, is that a few days ago, I mean, I got this plot from Roger Bilhem that was, this is a creep meter that is set on the North Anatolian fault, and that has been kicked by the two earthquakes that happened, I mean, the 7.8 and the 7.5. And it's quite impressive. This is happening at 500 kilometers from the source of these two earthquakes. And well, now we start not caring very much of what, I mean, about the dynamic triggering that took place within the creep meter for the earthquakes itself. But if you look at the post phase between the two earthquakes, I mean, you see a sort of prolonged triggered slip, or the gauge material, and this goes back to my courses in rock mechanics, may remain perturbed over multiple slip cycles and with these discrete events that are following the triggered event. And I think that this is a huge deal of knowledge that we will be gaining after this earthquake. I'm not just talking about the near field of this earthquake, but the far field is already exciting. And I really look forward to see some fresh news from this earthquake sequence. Of course, the past studies are equally important. Always throwing here a very nice slide, and that is coming from Nick Ambrazis in 1971, that shows how the East Anatolian fault, on which the two earthquakes, the two large earthquakes took place, was quite inactive when you compare it to the Northern Anatolian fault. So here where I'm taking you from a very short-term behavior of a fault that is far away to a sort of a long-term behavior by summing up the seismic strains from historical earthquakes over a period of time of 1,600 years. That gives you a better understanding of long-term processes within your earthquake cycle. And of course, when we talk about Turkey, I think that it's always nice to give credit to Nick. Nick was a mentor for me, and Nick has been doing a great work. And there are two other people that I like also reminding anytime we talk about Turkey, are Aykut Barka, who's an earthquake geologist that passed away, unfortunately. And Rob Reilinger has deployed a huge amount of GPS instruments, Rob from MIT, and these guys, they have thrown grounds for all the understanding that we have now. And it's now the new generation, the new PhDs will definitely clarify all what we see. I mean, as these funny behaviors that we see here, and we see something very similar within the ridge crust that took place on creep meters that happened at 300 kilometers far away from the two sequences of the two large earthquakes that happened in California as well. So then myself, I decided to forget about my rock mechanics experiment, and I moved to the scale of the lab, of the natural lab, which is the scale of the lithosphere. And I think that now this word is becoming quite used, lithosphere scale rock mechanics experiment. The first time I heard this was from Roland Bergman. And what you see on your left in the picture is a very simple picture of a triaxial test I was used to play with. And on your right-hand side, you see a beautiful flexural slip that is cutting the surface of the Earth following the 1980 Al-Aslam earthquake. Then what we try and do is to chase deformation. If we're lucky and have instruments prior the earthquake takes place, then it helps a big deal, or run immediately to the field and then try and collect data sets and establish geometries and initial boundary conditions. And here, myself, I'm a big fan of surface geology. I think that anything that we do, geology is always a landmark. I mean, it tells you the ground truth. It gives you the final picture. If we do not understand that picture, then I think that if we may be abusing of our physics and computers and so on and so forth. So real data sets are extremely important. And then parameters of faulting, the seismology gives a very good constraint on this, and I will show it in a few minutes. And myself, I keep arguing that understanding the Earth structure before getting yourself embarked in GPS, in sophisticated interpretations of your GPS velocity field, might be misleading. So it's extremely important to use seismology before we move on and try and understand other type of data sets. Then the relevant deformation measurements are also time dependent. I mean, longer you have, I mean, better it is. I mean, now we're in the era of continuous GPS, and paleoseismology remains an extremely important data sets, and we will see this in the Himalayas. And later you could use models to resolve faults in rock and constitutive properties. I like very much viscoelastic modeling. I like very much rate and state friction laws when it goes to discontinuities. And this would allow you to build a physical model for strain accumulation that may carry, I don't like the word predictive, but here the predictive is just for the space, the stress pattern over your space domain. So myself, I did a PhD in beginning in strong ground motion seismology with implications on active tectonics. Then I rely on a number of methods in here. And some of these methods were initiated by some of my former PhD students, or they relied on existing methods and then they a little bit refined them. I like very much strong motion inversion. The code that we're using specifically here has been readapted by Malik Momani, that is now at EPFL. He's a former PhD student of mine. I'm a big fan of matched filter detection, high resolution earthquake detection and location. And I'm referring here to a former student of mine as well, Blaž Vicic. And I'm also a big fan of GPS analysis, but not done by myself. I'm a biased seismologist, but done by a friend of mine and a collaborator, long-term collaborator, Alessandra Borghi. She's a GPS geodesist, and she has not a single slip factor in her mind anytime she looks at GPS data sets, and which makes a big deal of sense. So, and Earth structure retrieval relies on, now there are a bunch of programs that you could use, and I always enjoy using programs developed by my former students. And this is a nonlinear Bayesian scheme that was developed by Surya Pashai during his PhD and further improved during his postdoc here at ICTP. And Surya happens to be the first Nepalese seismologist that we've trained, and now he's a professor at the University of Utah. And another code that is quite interesting to depict discontinuities within your seismic waves is using autocorrelations. You could use, of course, receiver functions. You could use autocorrelations, P-wave coda. And this is a code that was developed by Hariram, who is attending this. He's a former Nepalese PhD student now that started a postdoc here at ICTP. So I'm also a mechanicist. I try to be as broad as possible, and this goes back to initial works that I did with a former fellow that worked here as a PhD student. I was co-supervising him, and then he did a postdoc here, Ricardo Riva, that is now professor at Delft, modeling co-seismic and post-seismic deformation. We started using normal mode theory, and then we went into numerical schemes, a little bit more sophisticated numerical schemes that would allow us to chase the stress evolution of earthquake faults within their earthquake cycle, accounting for post-seismic deformation. The same code has been expanded a little bit, plugging into it rate and state friction laws. And we always finalize this with strong ground motion simulations. Working at ICTP is extremely, I think, challenging because I'm the only seismologist, so I need to be as broad as possible. So to satisfy the needs of fellows from developing countries. So I got back to some extent to the works that I was doing in my PhD and getting into the simulations of the wave field. And this is also through a former postdoc of mine, Letizia Fundutas, that is now at GNS in New Zealand. So if we get to the field now, this is Italy. Italy is a natural lab. I will be talking about Italy and the Himalayas. I will be taking you from a place in which basically the deformation is not very fast. I mean, here we're talking about 4 or 5 millimeters per year to the maximum, and then we will be going to the Himalayas, in which the rates of deformation are extremely high. I will argue here that external forces within the system are not that important. They are important. They have been important in shaping the big landscape. But right now, we'll see that the post-seismic phase and the buoyancy forces within the system are extremely important. Okay, Italy lies in a plate boundary between Eurasia and the African plates with velocities of convergence of few millimeters per year. And the deformation within this plate boundary is extremely complex. I mean, it does not reflect the motion of Africa. I mean, in Sicily, it does. While when we go to the Apennines, you see that it's much more controlled by maybe what is called by the anti-clockwise rotation of the Adrian promontory. And when we go to Adria, I think that the original works of Helen Anderson and James Jackson in 1987 are extremely useful, and with simple and well-constrained focal solutions at that time. These are works that we will never knock down. I mean, they are just they got things started, and we owe them this. And we recognize that on the Balkan region, we have more of strike, slip, and thrust faulting earthquakes, while on the Apennines we have extension. Then this block that is empty of earthquakes might be just rotating anti-clockwise and giving you a little bit of pushing convergence in the Balkan and extension along the Apennines. Of course, this picture has improved over time, and thanks to GPS velocities. These are the works of Nicola D'Agostino, just to cite one of those. I mean, he's a friend. So GPS geodesy has been now increasing over the Italian territory since 2014. We've got a boom in the GPS stations. Now, this has allowed Nicola to come out with to split the Adria into 2 microplates. I mean, what he calls the Northern Adriatic part and the Apulian part here, with a sort of a discontinuity in the middle that might have maybe implications within other interesting fields. So this is a kinematic model, but here there is a bad need of understanding the Earth structure beneath it. And then if you look at the initial work that were done by Omori, I'm referring, Omori is known. He's the guy that is behind the Omori law, and Omori was in Italy after the 1908 earthquake. And he came out with this wonderful picture of the segmentations of all these historical earthquakes that are taking place along the Apennine chain with gaps, or I mean, you could call these gaps. I mean, seismic gap has it's not a theory; it's basically a fact based on observations. Or if you would like to put a theory behind it, there is you could call this a stress shadow, as Ruth Harris would call it. Or, I mean, if you're a big fan of the very recent work done by Ross Stein in Nature Geoscience, but that applies to subduction zone, let's see whether this is the core or the corona of stress transfers between one earthquake and the other. If you look at the same picture from a GPS viewpoint, you see that the strains are really mimicking the locations of these historical earthquakes. And then if this is coming from Nicola D'Agostino, and then if you see, here are all the most recent earthquakes that took place along the peninsula that have been filling up the gaps or these holes within your seismic strains that were basically accommodated by earthquakes. But later on, we will look at these specific structures here since 1997 up to 2016 and try to understand what happens at the level of active faults. But before we get to the level of the active fault, let's try and appreciate the geometry of the structures of the lithosphere, asthenosphere, here beneath the Italian peninsula. Well, the most interesting feature that you may capture here, which might be a place that we'll be rapturing soon if we trust the way things have been going on, is this region, which is the Pollino region. And here, many years ago, I got a proposal accepted by the Italian Ministry of Research. We deployed GPS instruments, and we came out with, in the Pollino region is an extremely interesting place. You have huge normal faults with impressive offsets at the surface that you see here. And Daniela Pontosti and Francesca Cinti from INGV have been digging trenches across these faults, and they came out with paleo earthquakes that were going back something like more than 1,900 years ago. And while this place is quiet from a seismic viewpoint, I mean, the GPS that we've deployed many years ago, that we published a paper in Geophysical Journal, were at least 4 times the trenching data sets. So what is missing here, in fact, is the Earth structure at some point when we started doing all this work. If you look at the initial Earth structure here, you would look at papers by Piero Malo, by Morelli, Andrea Morelli, and Spackman, where they give you a little bit of a long wavelength understanding of the structures in here. And then afterwards, in early 2000, we started looking at the surface waves, and what you may just look, this is your peninsula, and then you see that Pollino, for instance, happens to be within a sort of what we call a slab window. So it's quite interesting to understand the connection between shallow processes and a little bit intermediate processes within your lithosphere. And this is something that we did also along specific transects across the peninsula following the 1997 Umbria Marche earthquake sequence. The 1997 Umbria Marche earthquake sequence is quite famous because it has knocked down, unfortunately, the one of the most beautiful churches in Italy, which is the Assisi Church. So if you look at the transect here, across the peninsula, okay, these are the earthquake sequence that took place in 1997, magnitude 6. It's a doublet. We have always these 2 earthquakes that are taking place, one after the other one. And there has been plenty of dip seismic sounding profiles that we use that would allow us to have, to constrain our crust, so better resolve what was going on at larger depth. And this is coming from PhD thesis of my first PhD student in Italy, Giordano Chimera, where we've seen that your crust is basically decoupled from your lead with a low velocity layer here. And this is a sort of a scheme that you would, that maybe, that could be called as it's like a delamination process that you see here. And you see the intermediate seismicity that happens beneath the Umbria Marche region. So the seismicity goes between 50 and 120 kilometer. It's not distributed along a Benioff zone, but it's really distributed all across the thickness of your lithosphere. And what we did, so further to this image, then we basically got into density estimates by using gravity data sets and heat flow and viscosity estimate. And this goes back to a paper we published in 2007 with Ali Ismail Zadek many years ago, where we've seen that the crust and the deformation here in central Italy seems more to be explained by a delaminating process and buoyancy forces rather than by external forces. I'm sure that external forces are contributing, but it seems like the bigger scheme is. And this scheme basically explains also one of the dilemmas that exist in Italy, and which is extremely interesting, is the existence of very external compression here when you go to the Adriatic part, and the localized extension that we see here right beneath the peninsula. And since 1997, I moved to GPS. I moved to GPS as a fun user of data sets, but not as a space geodesist myself. So relying mainly on a team from Polytechnic of Milan, with whom the collaboration has been extremely useful and fruitful over the years. This is the first permanent GPS that I've set myself. I was doing the hard work. So I was going to the field and digging and putting, setting monuments. I was a rock mechanicist, so I knew how to locate rocks that were quite stable. And this is extremely important if you would like to chase deformation within low rate regions. And this is a Trimble, just not to give to advertise Trimble. This is a permanent station with a chalk ring that is set on a pillow lava. And this station was set, I set the station in 1998, and it's still online since 1998. These are one of the first stations, permanent stations that I've set, and it's on the Italian Space Agency website. And what we've been doing also, we were extremely careful, and we were always doing spirit leveling on both permanent sites and campaign sites. So here you see campaign sites that we deployed in many regions in Italy, and just to make sure that we do not have any side effect. So out of these studies, we came out with a number of papers in which we've been trying to look at, to have a little bit of a feeling of what the effective viscosity within the crust and within the mantle could be within the lower crust. And these are a number of papers that we did. And here with Riccardo Riva and Alessandra Borghi, we came out with some quite interesting results after Umbria Marche, in which we said that the argument was that the fact that there was a sort of an intracrustal low viscosity region, 10 to the power of 19, that was controlling the viscoelasticity. But in 2007, with Riccardo, we've seen an extremely long-lasting afterslip following the Umbria Marche that was more explained by a sort of a discontinuity that could be right beneath the seismogenic layer. So this was a Geophysical Journal International paper that was quite interesting, because we were arguing that there might be a shear zone beneath the seismogenic layer, further to the low viscosity layer that was in there. So in 2015, we got a booming within the GPS data sets. Then more data you have, more GPS data you have, then maybe more important is the understanding of the Earth's structure. And at the same time, we wanted to look at the Adriatic plate and all the system there. And bathymetry data sets started popping up. If you look at, this is the bathymetry of Adria, and Adria is right here. Okay, then what you see in white is the peninsula. What you see in color, this beautiful DEM that was computed by Federica Follini from ISMAR in Bologna, shows that the topography is not, that the bathymetry is quite disturbed within the central part of the Adriatic Sea. So then the understanding of the Earth structure. So, you know, seismologists in the 90s, we were always removing noise from the signals, and then later on we discovered, I did not discover, others did, that ambient noise is extremely useful in understanding the Earth, and it was optimizing a little bit the classical work that we were doing from earthquake seismic tomography. Then getting into ambient noise was quite useful. And these are the works I started doing together with my PhD students. Two of them, one is from Ghana, Daniel Manumarfo, I did his PhD here, and a student from Algeria, Radia Kharshoush. Radia was looking at the Adriatic Sea and at the Adriatic plate, and Daniel was looking at the peninsula and the Tyrrhenian Sea. And the plate boundary in the Tyrrhenian revealed quite interesting results, if I have to go ahead. And the existence of, this is a section that goes from Sardinia down to the Calabrian arc that shows the existence of a very low velocity layer here. This is a 4.0, 4.1 VS, and all this was basically extending all over the paleogeographic reconstruction of the Calabrian arc in time. It's like it's the signature within the Earth structure of all the path that basically stands behind the retreat of the Calabrian arc. So this is at the bigger scale. At a larger scale, we came out with the conclusion that maybe now, even from the geometry of the physical properties here within the Tyrrhenian Sea, it seems like the African motion is taking over the retreat of the Calabrian arc. And this came out, this is maybe one of the reasons why it came out in Nature Scientific Report. And we've seen that crustal depth depth. There are exhumed mantles at very shallow depth, and all these exhumed mantles, they seem to be right beneath the system. One of the largest, Vavilov and Manyagi Vavilov is the largest volcano in Europe. I mean, in terms of extent, that is beneath the Tyrrhenian Sea. Then later on, we started looking at the Adriatic plate, and we were lucky because we started collaborating with colleagues from Croatia, looking at group velocities and phase velocities, and going here, group velocities up to 40 seconds, phase velocities up to 70 seconds, that would allow us to have a really an interesting understanding of the Earth structure beneath what was called as the Adriatic promontory. And here are quite interesting sections that you may see across the Adriatic, okay? And what you see here is that the lithosphere is not that uniform over its extent. I mean, at least over the northwest, southeast direction that you see here. And you see that the lithosphere is exactly this one. Here we see the necking of the lithosphere beneath the Alps, and then here we see a thickening in the central part of the Adriatic Sea that is quite interesting. And to some, the B1 is this one as well. Here you see it's like a sharp discontinuity within the physical properties, but I don't want to over-interpret this. Okay, here it's here we're talking about 4.5. This is very high velocity. This is reasonably, it's not that very low. It's 4.3, 4.2. Here it's it's less. It's around 4.1. Kilometers per second. Then the lithosphere seems to be quite heterogeneous along the major extent of what was considered as the Adriatic promontory, a single plate, and then split into 2 microplates by Nicola D'Agostino with GPS data sets. And of course, we have also other observations that I would not slab gap when you go towards the northern part, right beneath Trieste. So the Moho picture is quite interesting. I mean, it shows, I mean, this is this high thickness of Moho is the place in which Moharovicic has discovered the Moho, by the way. And you see this extremely high thickness of the Moho coincident with a place in the right beneath the Adriatic, closer to the Croatian coastlines, in which the lithosphere increases its thickness. And then you see that the Moho is not also that homogeneous. I mean, we do preserve to some extent, but the central part of the Adriatic seems to be the place where things are quite are worth investigating. And of course, we have earthquakes here as well. I mean, we have shallow earthquakes that are more of strike slip and thrust faulting, and it's quite interesting to look at these events as well, the few earthquakes that we have in there. If you plot, then if Radia has plotted here the thickness of the lithosphere and versus the bathymetry, you see that the lithosphere beneath the Adriatic Sea is thickening. When it goes to the north, it's like a normal lithosphere, and while here it gets into like a subduction zone, and this subduction zone has been already observed by Wim Spackman and our colleague Claudia Piromalo and Andrea Morelli, but this thickening right beneath the Adriatic was not reported. And on the southern edge, it seems like this very high gradient within the thickness of the lithosphere before it becomes sort of a normal lithosphere coincide with a quite important strike slip, which is the Gargano strike slip here that gets into the Adriatic Sea, that has been chased also over seismic profiling data sets and so on and so forth. If you take this velocity model and put it in density, these are using PyLith. These are runs that were done by a former PhD student of mine, just to look at the buoyancy effect, but without getting into any data fitting, just plugging it using Naif and Drake, and then look at the flows. I mean, we see interesting features here. I think that if this is a section that goes from the southwest to the northeast, then this way, okay, it goes like this way, southwest up to the northeast, you see that it's like it's subducting beneath the Alps. But here, there is something going on. I mean, you see this large, thick lithospheric body is like downwelling, and then you see it clearly here, like a downwelling object. And then if you simulate the your velocity field out of your velocity structure and trying to compare it with the GPS data sets, we do quite reasonably well without any data fitting. We do not do very well here in the southern part, but at least from here up to the north, it's where in all the places in which the compression is chased along the external front of the Italian peninsula. And here you see the GPS, the vectors that are reconstructed out of the simulations. You see a faster velocities and smaller velocities that would extend the Apennines here, and that would in some way compress the external part. This regards the plate boundary, and now we will a little bit move to the scale of the faults. And Italy has been, Italy is always active. It's like we're having earthquakes on a 5-year base, and since 1997. We've been chasing these earthquakes over time. And one of the most interesting earthquakes that revealed quite interesting, both from a science and a communication viewpoint, is, of course, this earthquake. It's the 2009 earthquake. And this is a geophysical journal paper that we published long time after the earthquake. And although this understanding of the existence of a slow slip prior to the earthquake was, to tell the truth, was recognized from the GPS data right after the earthquake. And for obvious reasons, we did not want to add to the big problem that happened in L'Aquila. And we wanted to publish this paper in a peaceful time. And what happened here, if you look at the GPS data sets, the blue ones, this is the fault, this is Campotosto fault to the north, and this is Paganica to the south. And what you see in blue are the interseismic velocity, the interseismic displacement field, velocity field, and what you see in green is the slow slip that we've captured. And this is a slow slip that happened around mid-February, and we think that this slow slip has taken place along a décollement that is beneath the L'Aquila fault, but not only beneath L'Aquila, but even beneath Campotosto. This was a sort of a 6.1 magnitude slow slip that took over a time of, we think that this has taken place over a time of 2 weeks. And if you simulate the slow slip, you would definitely fit the far larger extent of the aftershock sequence that was completely off fault here to the north. And the aftershock sequence of L'Aquila was quite peculiar. It was not conserved around the main shock, but it went to the north. And this was, a very simple Coulomb failure that was explaining the extent of the sequence. And further to this work, I think this got us back to the work that we did with Ricardo and Alessandra many years ago in 1990, following the 1997 earthquake. And here also, this thinking that there is a basal shear, there is a sort of a discontinuity, how thick it is, that's a big question. Beneath the normal faults came out from high resolution earthquake locations done by Valoroso Italia and GEO in 2013. And then you see this listric shape that is coming out of the seismic profiles. And this is a work by Oreca et al. And we've seen something that is extremely similar also from seismic tomography, from the inversion from a very high resolution tomography study that we did across the Umbria market, where you see really a beautiful anticline, but this is what I call a seismological anticline. You see it from the physical properties of the different layers that exhibit sort of anticline shape, but with a listric geometry. And it's a reactivation of the paleothrust. And this joins also the thinking that we had many years ago, that we had a long-lasting afterslip that was going on after the 1997 on a décollement beneath the 1997 earthquake. So the slow slip that we've looked at in L'Aquila was also highlighted within a work that was done by a former diploma student of mine, Florence Ramirez, an outstanding student from the Philippines that did her diploma here and that just finished her PhD, but in something completely different. And she did not pursue the tectonic tremor chasing using frequency scanning or backtrack methods like those ones developed by Poyata et al. And we did this, and we've been chasing the tremors in 2000, following before the sequence, before the 2009 sequence, and this is what we came out with. First of all, I would like to clarify that this title has been a little bit proposed by the editor-in-chief of Geophysical Journal. At that time, we did not want to put the word precursory. He insisted that we should put the word precursory. I mean, we said that the slow slip promoted the L'Aquila earthquake sequence, but we do not. I'm not a big fan of earthquake prediction, but I'm a big fan of the physics of earthquake prediction. And if you look at this plot, which is the plot that was published in Geophysical Journal, here you see the principal component over a number of permanent stations that show this gradient over 2 weeks' time within in the period of February. And this gradient coincide with an increase of seismicity that was done by, basically done by Valoroso et al. And this also coincides with a change within the VP over VS ratio in a paper by Lucente et al. In Geology, in which they focused all their because the paper, of course, was published prior to ours. They focused more on the foreshock that took place before the 6.3. And an extremely interesting result that we've never published, unfortunately, and Florence has left, and maybe we can consider publishing it, is the extreme and highly increase within the tremors and the low frequency event within when the slow slip was taking place. And further to this, the slow slip coincided within another work, and completely independent work, that was chasing the repeaters by Sugan et al. In GRL, where they've shown that within the same period, within the 2 weeks in February, the repeaters basically moved with 0.5 kilometer per day closer to the epicenter. And here we see that the epicenter, as it is shown along this plot as well here. So then the slow slip is there, and we're very much convinced about it, and we think that it has taken place on a shear zone. So we were excited by this, and so we pursued a little bit the whole work on all the exciting earthquakes that took place later on, looking at the 2016-2017 earthquake sequence. And this is a GRL paper we published with a former PhD student of mine, Blaž Vicic. And here we used seismological stations, and we used GPS stations on one side and seismological stations on the other side. We did high resolution earthquake detection. We did GPS chasing, looking at time series, and we did strong ground motion inversion of moderate sized earthquakes that took place on Campotosto specifically. And Campotosto is, it's an interesting fault. It's a fault on which it's right in the middle in here, and it's a fault on which people continue to argue that maybe a magnitude 7 can take place. And if you look at the plot of all the detected earthquakes, you see a shed down at 10 kilometer. This is basically done along the shear zone here. I mean, these plots are done by Blaž along the shear zones. And then here you see, these are basically earthquakes along the faults, and what you see in here in this plot are along the shear zones. And then if you look at the inversion of the Campotosto earthquakes that took place, a number of earthquakes, you see that it's like there is a listric form. I mean, the dipper ones exhibit shallower dip, and this is quite well constrained. And at the same time, I don't know why it doesn't move. Okay, and then at the same time, we've looked at the evolution of the repeaters along the strike from the Paganica up to Montevettore, spanning all the different earthquakes and chasing this from 2009. And here you see the large number of foreshocks that were expanding over a very wide region, and in which even other earthquakes took place later on. So the main results of this, just to make the story a little bit short, is from the GPS viewpoint, is that the principal, apart this one, there is an outlier within the signal within the principal component analysis. We see that on Campotosto there was a sort of transient that took place first by the end of 2015, and then on another fault, which is to the north, Viso, there was another transient that was starting on, and till we got a transient even on Alto Tiberina fault. We've seen 3 different transients, and we still do not know the physics behind these transients. They are there. I think we were not the only ones to look at the GPS time series, but of course, I mean, the direct and my speculation about this is maybe they might have a connection with the shear zone. The high resolution detection and location that was done on the shear zone, here you're looking at the shear zone along strike over a distance of more than almost 150 kilometers down from L'Aquila up to Alto Tiberina. As you see the segmentation over time within the microseismicity, within the tremor behavior. And this is telling us, this has confirmed the listric geometry of Campo Tosto. And then we see that the high rate seismicity that you see in here are the places in which earthquakes are not taking place, where the slow rate seismicity segments are those ones that accommodated the large earthquakes that took place in this region. Well, the interpretation is that there are different mechanical properties along the segments, or some of the segments might be connecting to listric faults, and some of the segments might be connecting to maybe high angle normal faults. And this is another feedback that we got from the reviewers. So this said, what we're trying to do now is we're looking at permanent stations along the strike, trying to have a feeling with the post-seismic deformation. And these are really, sorry for the plot here. I mean, we're looking at the, trying to look at the GPS time series in terms of post-seismic deformation. Please, those ones that are available and that are accessible to us. So this said, I would like to move to very fast to the Himalayas, moving to a very large, to a little bit different length scales and different boundary conditions, different faulting geometries, and just always highlighting the importance of seismology before, I mean, how seismology can help us in understanding and having a little bit, and maybe closing up some specific discussions within the Himalayas, although I think that all the open issues are still there. This is a very nice plot from Roger Bilham, from my dear friend Roger, and I think that everyone knows the paper where you see here the seismic budget along the Himalayas and the location of the Gorkha earthquake, and these big earthquakes that are along the strike of the chain. And what the thinking here would maybe is badly needed at this level is really along all these conceptual models of Roger is to have seismological sections and geodetic sections, and also paleoseismological investigations towards the leading edge to decipher and understand the maximum expected magnitude and maybe the earthquake generation processes beneath the Himalayas. So if you work in the Himalaya, I think that it's clear. I mean, it was not clear for many hazard analysts in the old time. I mean, hazard analysts were abusing a little bit of earthquake hazard. They were using seismicity that was within the higher part of the Himalayas and coming with B values without taking care of what, well, the record of the strain was released 150 kilometers down to the south. So you can't do hazard analysis without understanding all these length scale and not looking at the tiny seismicity to compute your B values. And here I'm plotting a fault scarp that was identified by Steve Wisniewski in India on the leading edge that would require a very large magnitude earthquake. And I always put this slide with a very smaller scarp just to explain scaling laws to students. And this is a fault scarp of a similar geometry. This one is a magnitude 7.3 thrust faulting earthquake that happened in El Aslam in 1980. And this is a paleoseismological paleo earthquake on the Himalayas. So the thinking behind all earthquake hazard, I think that Roger Bilham got it right, to my feeling. And these are the different scenarios that Roger keeps proposing over time. And you may have a maximum magnitude of 7.8 that would move one part of your décollement, and 8.5 that could put the other part of the décollement down to the south, or a full rupture of your décollement up to the frontal part where with a magnitude of almost 9 earthquake. But understanding the earth structure here is extremely badly needed. We started looking all these aspects in relying on Dehradun. This is a work that I did with Naresh Kumar. That was a Marie Curie postdoc here at ICTP, looking at the Western Karakoram Himalaya region, where with this beautiful section that looks like a crocodile. This is a crocodile shape, and this crocodile shape has been also identified from deep seismic sounding profile in the Alps. And this was the initial understanding that we had in this place. And now with Naresh, we're trying to extend this and get into putting more stations and really trying to get a very high resolution scheme on the geometry of the décollement beneath this part of the Western Himalaya. When the 2015 earthquake took place, then Surya was back. I mean, my former Nepalese student was back for a postdoc, and we took Hari Ram as a PhD student, and together with the University of Cambridge, thanks to the support of James Jackson, in the framework of the Earthquake Without Frontiers program, and working with Keith Priestley and Supriyo Mitra, was a large deployment of broadband instruments in the Himalayas that has been basically supplementing all the existing networks that were running in there. And this has allowed us a little bit to look at the geometry of the décollement using both ambient noise and autocorrelations of P-Kara waves. These are the different models. I think that this goes back to the original work of Nablak, that he was arguing that the décollement mimics a little bit the extent of a low velocity region that was also started initially with Pelka in 2005. So Harry looked at this region using nonlinear Bayesian inversion and then autocorrelation to depict the discontinuities. And we came out, just to make the story short, I would just get to the model here. Then we came out with a velocity. This paper is in press in JGR, by the way, Journal of Geophysical Research. We came out with this model of the décollement. Then India is here, okay, and this is the internal part of the Himalayas, okay. This is along this section. Then D is here. D is here. E is Tibet, and this is Tibet, and this is the extent of the block diagram that you see here. And this is basically what we think are the physical properties along the décollement on which the 2015 earthquake has taken place. We think that the high velocity is basically the, sorry, I need some water. We think that the earthquake has nucleated within a high velocity body, I mean, within the positive anomaly and the relatively low velocity. And then here we see that the earthquake tend to stop. There is a very important low velocity towards the décollement that might have a little bit promoted the arrest of the earthquake. And there is also an interesting feature, which is the low velocity region here, that do correspond to a reported low velocity rupture velocities of the earthquake, okay? Further to this, I think that the most important result, just to make it very short, are these sections. These are 3 different sections that are extremely important. One section is basically AA prime that you see here. Okay, this is India. This is still Nepal, but towards the Indian border. And these are the high mountain ranges. This is the mapping of the décollement that we did, and this is the duplex region that was recognized by other investigators. And this could be this is interpreted as the interseismic region over which the loading and the strain loading processes are taking place. If you look at the extent of the interseismic part before it connects to the channel flow beneath Tibet, the extent in here right close to the hypocenter of the 2015, and the extent of this interseismic part close to the 1934 are quite different. Then we're moving from a width of 50 to 70 kilometers north of the nucleation of the 2015 to almost 90 and 100 kilometers north of the source of the magnitude 8.4. If you use very simple simulations using the rule of thumb that Roger Bilham has defined, based on a very simple seismological rule of thumb, 100-kilometer interseismic patch would load with a low strain elastic energy loading on the décollement that would be equivalent to this type of magnitude, while a 50-70 kilometer would be equal to the exactly to the magnitude, the 7.8 that was that took place in 2015. So what we did together with Roger Bilham, and right after the earthquake, and we deployed GPS stations on the décollement, and then we've seen that we published this paper in Nature Geoscience. We've shown that the southward part of the décollement was locked over the 6 months. So this might be, I mean, you could interpret this as a place in which in which another earthquake would take place, or this would have to release in somehow a larger magnitude earthquake. According to the seismological investigations that we did here, this interseismic patch is happy with a 7.8. So now maybe if the future, I think that following the GPS along the southernmost part of the front is extremely important and would bring interesting results. And here, what is badly needed to constrain the whole picture is really trenching at the frontal part and understand whether these 7.8 are observed within the trenches along the strike of these profiles. I think that I will conclude here. I stop here. Thank you very much. I hope that it was clear. Cheers. Oh, shit. Do you hear me?
Yes, we do. Thank you very much, Karen. This was very interesting. So the floor is open for question. If you can unmute yourself, or you can add something in the chat.
Let me just switch on the video.
Any question?
That was clear. That was not clear at all.
Yeah, may I have one question? I didn't raise my hand. It's not. Yeah, yes. Well, firstly, thank you, Karim. Very high quality science and outstanding capacity building in our type of countries, obviously, which I'm grateful for you. Just a similar, not on what you presented, but it's just a case in point. The earthquake in Turkey, was it expected spatially and temporally? I mean, was it happened in a seismic gap, and was it also the return period of the event was expected? I mean, it's just a challenge for seismologists when tens of thousands of people perished. Can you remark on that? Thank you.
Oh, thanks. I think that, well, the word expected, I mean, depends on the time scale over which you're I'm sorry, this is, I think that everyone knows that the Eastern Anatolian Fault is an active fault. And I think that from the plot of Nick Ambrasis, it was very clear that this fault sooner or later would rupture, would transfer an earthquake. And from a historical data sets, it's clear that this is an active place. If you look at the landscape as well, I think that geomorphologists and paleoseismologists do agree that this is a region in which you would expect a large earthquake to take place. whether there were any, I don't know, GPS geodesy, detailed GPS geodesy that was done there, I really do not know. I know that much of, maybe at some point, maybe the little mistake that was done by some of our community, I mean, within our community, was to focus a little bit more on the Northern Anatolian Fault. Although the picture of neck embraces was showing that the Eastern Anatolian Fault was quite worrisome. I mean, it was clear that there was I mean, the time scale over which, if you compare it to the Northern Anatolian Fault, you would expect that sooner or later that period of quietness would stop. So I think that everyone knew that the faults were there, but people were still building. People were still building in a very bad way. So I mean, this makes us a little bit feel sad. And
yeah,
I don't know whether this answers your question.
Thank you. Yeah, sure.
But the rates of deformation along that fault are definitely smaller compared to the Northern Anatolian Fault. And it's, but I think that maybe the idea of this fault is also the fact that we have two earthquakes. Like it's bringing us like to the ridge crust. It's bringing us to the to other schemes here in right behind Trieste. We had two historical earthquakes that took place on the strike slip faults, one after the other one, and this was confirmed by paleoseismological digging, by paleoseismological trenching. And I'm sure that this earthquake will bring news, outstanding news in terms also of far field and dynamic triggering. And it's one of the most, it will be one of the most natural labs in the world for the next 10 years. So I think that for PhD students, it will be, I hope that the data will be open.
Okay, thank you, Karim. Is there any other question? Or you can put your question in the chat if you wish. Eleonore Rivalta said, thank you very much for the very interesting presentation. She had to leave, but she said she left a note.
Thanks, Eleonora. Thanks, Mehdi, as well.
Yeah. Okay, so if there is no other question,
thank you very much. Thanks, Catherine, for organizing this.
Yeah, I'm going to stop the recording.
Let's hope that we will have.
Yeah, thank you very much, everyone, for being there. It was really, yeah, an interesting presentation. Thank you.
Thank you, Karim.
Cheers. Bye.
Bye.
Thank you so much. Goodbye.